So today we'll be talking about acceleration and gravity. And the first thing I want to start with is acceleration is defined as the change in velocity, delta v, over a certain change in time. So that means, let's just say our change in time is t seconds. That means the final velocity, v sub final, minus the initial, which is v sub I, over that time will give us our acceleration. And this is our acceleration over that time. And usually in AP Physics 1, acceleration is deemed to be a constant value that doesn't really change. So you don't need to worry about jerk, and jerk is the change in acceleration. So we don't need to worry about that in AP Physics 1. So the next thing I want to mention is that we have to remember that there's a kinematics equation for a lot of things. And in kinematics, there are the big five, but in this scenario, we're only going to need to learn one of them, which is the kinematics equation. V final is equal to V initial plus AT. And this is pretty obvious if you're thinking about it with what our definition is. If we work with our definition, multiply both sides by t. This gives us V final minus V initial is equal to AT. So V final must be equal to the initial velocity plus an acceleration over a certain amount of time. And that makes sense. So let's do a quick problem using this concept. So a cart is rolling along a frictionless plane, spelled plane wrong, at 2 meters per second. A force accelerates it for 10 seconds. Its final velocity is 12 meters per second. What is its acceleration? So we ought to start by finding what we know. So we know the original speed, which is V naught or V initial. So these are usually interchangeable, is equal to 2 meters per second. And we should probably write down our kinematics equation just to be make sure we know what's going on. So we know that V final is equal to V initial plus AT. So from here, we know that the time was 10 seconds, and we know its final velocity is 12 meters per second. So if we fill this out, we actually know that the only variable missing was a, which means we can solve this kinematics equation. So we have 12 meters per second is equal to 2 meters per second plus AT, and we know that t is 10 seconds, so we're going to replace that. And this gives us 10 meters per second if we subtract V initial like this, divided by 10 seconds, is equal to A. And then this becomes, the seconds stays on the bottom over here, and this becomes 1 meter per second squared equals A. And that's how that works. So now, the thing is, acceleration, like any other vector, has a direction. And it's important to note this. So if we think about it like this, if we draw a chart, give me 1 second. So here's the chart, and you might want to copy down, or if you don't, it's fine. So the question is, if an object is moving to the right, which I will define as the positive direction, so I'm going to draw my number line here. If we have 0 here, we're just going to call this the positive direction and this the negative direction. If something is moving to the right, so v is positive, that means velocity is positive, and we accelerate to the right, as I mentioned, acceleration has direction, what happens to the object? So in this case, it gets faster. But what if acceleration is to the left and it's moving to the right? So as my cart is going this way, it's moving this way, a force opposes it and tries to slow it down. So this means it must be slowing down like that. And if you notice, the signs do matter. If the sign of acceleration and velocity are the same, when the acceleration is applied, the object goes faster. And the opposite is true if the acceleration is the opposite direction of velocity. So this is going to be slower if it's moving to the left and the acceleration wants to pull it right. And if acceleration is to the left and the velocity is also to the left, it will get faster. And I should note that faster in this case, faster means speed increases, and slower means speed decreases. Not necessarily velocity decreasing or anything like that. It's speed. So yeah, that's just all you need to know. So just remember that an acceleration does not always mean the object is speeding up. And we will see this in practice very soon. So the next big concept is the concept of g. And you might have seen this a lot. So g is defined as the acceleration due to gravity on a planet. And usually g refers to the gravity on Earth. And more specifically, at Earth's surface. We will see in Unit 3, Gravitation, that the force of gravity does actually depend on distance away from the center of mass. So it's important to note that g, in our all intents and purposes as of now, is the acceleration due to gravity at Earth's surface. And since Earth is really big, naturally you'll think, if this is Earth and we're here, the acceleration only really changes if you move a lot, like really far away or really deep into the Earth. It's at the surface, if you zoom in really far, here's us, little human, and if we just throw something in there and drop it, everything that we visualize will be at this value of g. And you might be wondering, what is g? Well, at the surface of the Earth, g is equal to approximately 9.8 meters per second. And this is all you need to know. And it's important to note that you should always use 9.8 meters per second and not 10 unless otherwise stated. So if it says just approximate, you can approximate this to 10 meters per second. There's no problem with that. Unless it explicitly tells you to use 9.8. And obviously, 9.8 is just more accurate, and you do have access to a calculator, so I wouldn't see why you wouldn't use it. So, yeah, that's all you need to know. That is what g is. So let's do some problems. But before we get to that, there's one more kinematics equation I'll quickly teach you. And it's that the distance, or displacement actually, to be more exact, which is equal to delta x, is equal to 1/2 times the acceleration times the time squared plus the initial velocity times t. So this is an important kinematics equation, and it is one of the big five, and it's just important to know. So you don't need to memorize any of these kinematics equations. They're all given to you on the formula sheet that is provided by the College Board, but the more you can memorize these equations, the quicker you can solve problems because they just come to you and you don't need to ever look at the paper again. So let's do a problem. So a rock is dropped from a height of 20 meters. Find how long it takes to reach the floor, and B, its velocity right before hitting the ground. So this seems like not a lot of information. Like, all we're told is the height of the object. Like, don't we need to know its mass or something? Well, okay, the first thing to note is that gravity accelerates all objects at the same acceleration. If you remember that famous experiment, if you drop a bowling ball and you drop a feather in a vacuum chamber, since there's no air resistance, they'll both hit the bottom at the same time. The acceleration experienced by objects due to gravity does not depend on its mass. So no, we don't need to know the mass. Now, B, how are we going to even solve this in the first place? So let's just start with part A, and let's do some kinematics equations, actually. Let's write down our kinematics equation of D is equal to 1/2 a t squared. So how are we going to find this? Well, conveniently, we do know what d is. D, which is displacement, which has a direction, is given to us. It's negative 20 meters. And it's not 20 meters, remember, because it's falling downwards. So its original position is here, and if I'm calling downwards negative, it drops by 20 meters. So it's negative 20. And we're also given acceleration to be 9.8 meters per second. But there's a caveat. It has a negative in front of it. Thankfully, these two negatives are on opposite sides of each other of the equation. We can just cancel them out. So we get 20 meters is equal to 1/2 9.8 meters per second times t squared. So solving for t squared, we get 40 meters divided by 9.8 meters per second squared. And if we use the calculator real quick, this is going to give 40 divided by 9.8 is equal to 4.082 seconds squared. And notice how the seconds is still squared, because then we take the square root to find that t is equal to 2.02 seconds. And that's only for part A. So we got to move on to part B. Part B is asking, find its velocity right before hitting the ground. Well, we remember that final velocity is equal to initial velocity plus a times t, right? And what's convenient is, since it was dropped from rest, I should have mentioned this is dropped from rest, we know that v initial is 0. So we can conclude that v final is equal to acceleration times time. So if we know that our acceleration is negative 9.8 meters per second squared times 2.02 seconds, we can find that v final is equal to, put in the calculator, 19.8 meters per second. Oh, but I'm missing something. A negative, because remember, we are falling downwards, and velocity is a vector with direction. So never forget that negative sign. So that is all for today on acceleration and gravity. Next, we will be talking about the big 5 kinematics equations.